Let's take a look at example 3. We're going to use the curve y squared plus x squared equals r squared to prove that the surface area of a sphere with radius r is 4 pi r squared. This is a really cool application of these surface area integrals. This equation here, y squared plus x squared equals r squared, this is the equation for a circle centered at the origin with a radius of r. And we can imagine spinning that circle around an axis to form a sphere, and we'll use these surface area integrals to find that the surface area of the sphere is 4 pi r squared. So first of all, we want to draw the equation of this circle. We have x squared plus y squared equals r squared. So here's the picture of that equation. This radius distance is r. And if we think about spinning this about an axis, we would form a sphere. If we spin the entire thing, then we'd actually be spinning around twice in some sense. So we're just going to take the top half of the circle and spin that around the axis. Otherwise, if we're spinning the bottom half around as well, then we're really getting twice as much sphere as we want. So all we're interested in here is the top portion of this sphere. And we can obtain this by solving the given equation for y. So I can write y squared equals r squared minus x squared. So y equals the square root of r squared minus x squared. This equation gives us the top half of the sphere. So we get this here. This is the equation y equals the square root of r squared minus x squared. We will revolve this equation about the x-axis to form the entire sphere. Now let's think of the x values here for the limits of integration. The radius is r, so this x value here is negative r. This x value here is positive r. So we're going to integrate from negative r to positive r when we set up the integral. Let's take a look at this just to make sure we're understanding how this works. Let's take a look at this in some graphing software. So here's our curve y equals the square root of r squared minus x squared. And to form the sphere, we are going to rotate this curve about the x-axis. When we do that, we get this. So using the surface area formula for a surface of rotation, we will find that the surface area of this sphere is 4 pi r squared. So now that we have a better visualization of this sphere, let's go ahead and work through the process to find the surface area. And we'll draw in here sort of what the sphere looks like. So something like this. We're imagining rotating that graph again about the x-axis. So there's a rough sketch of the sphere. All right, we want to first set up the surface area equation for rotation about the x-axis. So this is where we start. We're not worried about if we integrate with respect to x or y or any of that. We're first just going to write down the equation for rotating about the x-axis. So surface area for rotation about the x-axis is 2 pi y dl. And now we have a choice. We want to determine if we use the dl expression that has integration with respect to x or integration with respect to y. For this problem, since we're going from x value to x value, and since we have an equation for y in terms of x, it's going to be easier to integrate with respect to x. So we're going to use the expression for dl, square root of 1 plus the derivative of y with respect to x squared, and integrate with respect to x. So let's find the derivative of y with respect to x. So we take the derivative, dy dx, and that's the derivative of this square root expression. This is going to involve chain rule. R here is simply a constant. So we first take the derivative of the outer function, which is the square root. The derivative of the square root is 1 over 2 times the square root. And we just put in here exactly what we had as the inner function previously. We're using chain rule to take this derivative. By the way, I'll just mention that this is something we really want to be comfortable with. If you feel a little bit rusty on the chain rule here, then you should take some time to review this and make sure that you're comfortable with the different steps that we do here. Okay, so we first take the derivative of the square root. That's 1 over 2 square roots, and we put the inner function in here. And now we have to multiply on the outside by the derivative of the inner function. Remember, r is a constant, so the derivative of r squared is simply 0. The derivative of negative x squared is negative 2x. So we multiply here by negative 2x. We can cancel the 2's, and we can write this just a little bit more simply as x, negative x rather, divided by the square root of r squared minus x squared. Here's our expression for the derivative of y with respect to x. We're going to put that here into the integral, and we're going to square it. So the square root here will go away, and we'll have negative x squared. So let's progress with our integral. So surface area is the integral of 2 pi y, and now dl is the square root of 1 plus dy dx squared. So let's just do that in one step. Let's put this in here and let's square it as we do this. So we do the numerator squared. Negative x squared is just the same as positive x squared. We can just write that as x squared. And then in the denominator, we have this square root that we're squaring. So the square root gets undone, and we just have r squared minus x squared. Integrating now with respect to x. So here's our integral so far. Let's put in the limits of integration. We are integrating with respect to x, so the limits will be these x values from negative r to positive r. Remember, r is just a constant, so it looks a little bit messy, but r is just some number, whatever radius value we would like. Okay, so far so good. What's our issue now? Well, we're integrating with respect to x. We've got a lot of x's in here, but we have this other variable y. Y is not constant, y is a variable. I need to get y here in terms of x, and I can't just write x instead of y. If we just wrote an x, that would be rotation about the y-axis. That's not what we want. So we need to write the equivalent expression for y in terms of x. That's this expression here. So we replace y with this square root of r squared minus x squared. So we integrate from negative r to positive r, 2 pi times the square root of r squared minus x squared times the square root of 1 plus x squared divided by r squared minus x squared dx. Take a look at this integral. Doesn't this look kind of terrible? It looks really messy and really difficult, and just this is intimidating at this step. And I wouldn't blame you if you wanted to just stop here, maybe throw this into a calculator or something and evaluate it that way. But this one we can actually solve by hand, and it's not as bad as it looks, I promise. So what can we do here? I have a square root times a square root. I can join those both together under a single square root. So I'm going to multiply everything inside this square root and essentially distribute it to both of the expressions under the other square root. When we do that, a bunch of stuff cancels, and the integral becomes much simpler. So we're integrating from negative r to positive r, 2 pi. Now I'm going to distribute, since we're working with a square root times a square root, I can distribute everything under this square root to everything under the other square root. So we have one big square root, and we take r squared minus x squared times 1, so that's simply r squared minus x squared. And then check this out. R squared minus x squared times the second fraction, these will cancel, and we're just left with x squared. So we have plus x squared. Minus x squared cancels with plus x squared, and we have the square root of r squared. Well, square root of r squared is just r. So look at how simple this integral becomes. It's the integral from negative r to positive r, 2 pi r. We're integrating with respect to x. And look at this. We have the integral of a constant. This is just a constant that we could bring out front. We're really just integrating 1. It's pretty much the easiest integral that we could get. It looked terrible here, but it's simplified beautifully. All right, so let's continue on. We're integrating a constant. So the integral of a constant is 2 pi rx, and we're integrating from negative r to positive r. Using the fundamental theorem of calculus, first we'll put in the b, the positive r, then we put in a, negative r, take the difference. So we have 2 pi r times x, which is now times r, minus 2 pi r times negative r. Well, if we have negative times negative, that becomes a positive, so we can make that positive. And we have 2 pi r squared plus 2 pi r squared. That is 4 pi r squared. We just proved, using calculus, that the surface area of a sphere of radius r is 4 pi r squared. I think that's super cool. Just using this integral, which actually, the integral looked really complicated, but when we simplified a bit, it was actually a super easy integral. And we got this expression for the surface area of a sphere using calculus. I hope you think that's as cool as I do. This is a really cool example, I think. Finally, let's work through examples 4 and 5. We're going to be solving the same surface area for both these examples, but for example 4, we'll set up an integral with respect to x. For example 5, we'll set up an integral with respect to y for the same surface area. So we want to describe the surface area from rotating the curve y equals x squared about the y-axis now, and we'll go from x equals 2 to x equals 3. Now, this should look familiar. This looks sort of like problem 1. In problem 1, we had the same portion of curve, y equals x squared from x equals 2 to x equals 3, but in problem 1, we rotated about the x-axis. Now we want to take the same portion of curve and rotate about the y-axis. We'll get a different shape, we'll get a different value for surface area. Let's give it a try. So first thing we want to do is to graph what this looks like. So here's y equals x squared. My scale is going to be a little bit off, but we want to be able to visualize what this graph looks like. And we'll take a better look using some graphing software so that we get a more accurate picture when we've solved the problem. So here's x equals 2, here's x equals 3, so we're taking this portion of curve from 2 to 3, and we're spinning this around the y-axis now. So when we do that, we get a shape that looks something like this. Something like this. So we're taking the surface area of this rotated shape, rotating it about the y-axis now. All right, where do we start? We first start by writing down the surface area formula for rotation about the y-axis. We're not going to worry about integrating with respect to x or with respect to y or which variables do we use. We first simply write down the formula. So the surface area for rotating about the y-axis is this formula here. Surface area equals the integral of 2 pi x dl. This is correct. Rotating about the y-axis, we use 2 pi x. We want to think of x as the radius here of this shape rotated around the axis. Now we have the choice of which variable to integrate with respect to. We have an x here, but that doesn't necessarily mean that we must integrate with respect to x. We can choose to use the expression for dl that integrates with respect to x or with respect to y. For this problem, I think it's going to be easiest to set it up with respect to x first. And then actually the next problem, we're going to redo the integral, setting it up with respect to y, and we'll get the exact same number. So here we go. Integrating with respect to x, we use dl equals the square root of 1 plus dy dx quantity squared dx. So we're integrating with respect to x, so we'll put in the limits of integration from 2 to 3. We have 2 pi x. dl is the square root of 1 plus the derivative of y with respect to x, that's 2x. So we have 2x quantity squared integrating with respect to x. Now for many of these problems, our goal is to simply set up the integral. These integrals for surface area can be really gnarly. They can be basically impossible to solve by hand, or they'll use very advanced techniques that we haven't learned. So a lot of times the way to evaluate these integrals is to use a numerical integration method. Plug it in Mathematica, something like that. And a lot of times we're just interested in setting up the expression. This integral, though, we can solve, and it's good practice, so let's work through solving this integral by hand. So we have the integral from 2 to 3, 2 pi x. I want to simplify inside the square root. This is 1 plus 2x squared, which is 4 times x squared. How do we solve this integral? What technique would we use? Well, probably not going to use partial fraction decomposition. We're not going to use trig identities. We could maybe think about doing integration by parts, but I think the best method here is substitution. Notice that we have an inner function here, and the derivative of this is 8x, and we have a multiple of x sitting right here. So we're going to do u substitution. We'll choose u to be the expression under the square root, and that will allow us to solve the integral. So this is u sub, u equals 1 plus 4x squared. Let's work through the steps of u substitution now. We take the derivative of u with respect to x, that is 8x. Solve now for dx. dx equals du divided by 8x. We have a definite integral here, so we need to convert the limits of integration. These are x values. We need to convert them to be u values. So we do this in 2 steps. We say if x equals the lower limit of 2, then u is 1 plus 4x squared. So I'm going to plug in a 2 for x, and I have 2 squared is 4. 1 plus 4 times 4, I have 1 plus 16. U equals 17. Okay, do the same with the upper limit. If x equals 3, plug in 3 into this expression. So 1 plus 4 times 3 squared. 3 squared is 9. 4 times 9 is 36. Add 1 and we have 37. So these are the new limits of integration, 17 and 37. Now we're ready to write the transformed integral. We have the integral from 17 to 37 of 2 pi x square root of u, and now dx is du divided by 8x. So we replace the dx with du over 8x. Now we can cancel the x here. That's convenient. And I have the 8 in the denominator. I have the 2 pi. These are just constants, so I'm going to take those constants out front. 2 over 8 is the same as 1 over 4. So really I have a pi over 4 that I can take out. So I have pi over 4 times the integral from 17 to 37 of the square root of u du. Square root of u I could write as u to the 1/2, and we use the power rule to integrate here. The antiderivative of u to the 1/2 is u to the 3/2 divided by 3/2. So we have pi over 4 times u to the 3/2 divided by 3/2 is the same as multiplying by 2/3. All right, we can do a little bit more simplification here. We can simplify the 2 over 4. These cancel and I'm left with a 2 here. So I'm just going to write this as simply pi over 6 actually. So I have the 2 in the denominator, the 3, and pi in the numerator. So I'll write this, we need to integrate from 17 to 37. So I'll add this, and then pi over 6 times 37 to the 3/2 minus 17 to the 3/2. Here's our expression for the surface area of this shape. And this is approximately equal to 81.1. If we were to plug this into a calculator, this is 81.1. Once again, many times we will not be able to solve these integrals by hand. This one we could. It's good practice to work through a u substitution with a definite integral like this. And here is the surface area expression. Now, for the next problem, we are going to set up an integral that gives us the same value, but we want to integrate with respect to y instead of with respect to x. So problem 5, we're going to resolve the same area, but we'll integrate with respect to y. This is different again from volumes of rotation. When we did volumes of rotation, integrating with respect to x or with respect to y, that told us which axis we rotated around. For surface areas, we can set up integrals with respect to x or with respect to y, regardless of the axis that we rotate around. So even though we're going to set up an integral with respect to y, we have the same exact shape, the same surface area. All right, so we start integrating with respect to y. We start with the same surface area formula. The surface area rotated about the y-axis is 2 pi x dl. The difference is that we use the expression for dl that integrates in terms of y. So here we're going to use dl equals the square root of 1 plus the derivative of x with respect to y squared dy. Now, in order to get the derivative of x with respect to y, we have to solve the original equation for x. We did the same sort of a thing for problem 2, so we'll go through these steps quickly. To solve for x, we get x equals the square root of y. We're only interested in the positive value because we only have positive x values here for the curve. So now take the derivative with respect to y. It is 1 over 2 square root of y. Here's dx dy. We're going to plug that into this expression for dl and then write down the integral. So surface area integral is the integral 2 pi x square root 1 plus Now let's do this all in one step. We're squaring dx over dy. So imagine squaring this. If we square the 2, then we get a 4. And square the square root, we just get y. So when we square the derivative, we get 1 over 4y, integrating with respect to y. Now, what are the limits of integration here? Well, the limits of integration must be y values. We integrate from this height to this height. How do we get those y values? We plug in 2 and 3 into the function. So 2 squared gives us 4. That's the lower limit of integration. 3 squared gives us 9. That is the upper limit. So we integrate from 4 to 9. Now, we're almost there. We've got this integral expression integrating with respect to y. We have the proper limits of integration, but there's one issue. See if you can spot what the issue is. The issue is 2 different variables. We have x and we have y. We need to get x in terms of y. And we can't just write a y instead of x. That won't do. We need to write the equivalent expression for y, for x in terms of y. So here's what x equals in terms of y. We'll replace the x with the square root of y. So we have the integral from 4 to 9 of 2 pi times x, which is the square root of y, times the square root 1 plus 1 over 4y dy. Now we're not going to take the time here to integrate this by hand, but we could. And if we did, we would get approximately 81.1, the same surface area that we got from the integral with respect to x. So these two integrals, even though they look completely different, they are both equal. They're both describing the surface area of the same shape rotated about the y-axis. We can integrate with respect to x or with respect to y and get the same surface area. I highly encourage you to take some time, work through this integral by hand. It's good practice. It's not terribly difficult, and that will be a good exercise to work through. Actually, it's easier than the one that we did with respect to x. You get an easier substitution. So I would highly encourage you to work through that problem. All right, now that we've solved this surface area, let's take a look at it in some graphing software so that we get a really nice picture of exactly what this looks like. So here's our function y equals x squared. We're interested in the portion of the curve from x equals 2 to x equals 3, which is right there. And now we're taking that portion of curve and rotating it about the y-axis. So the shape that we get looks like this. Rotating around the y-axis, we get this surface, and we just found that this surface area of this shape is approximately 81.1.